your devices. Got a few top hat questions for you. We are recording. Just want to make sure that you all know that we are recording. All right. And if I don't say that at the beginning of a lecture, just raise your hand and say, did you remember to record? Because I want to make sure that I get everyone. All right. So let's start with this first one. This is from Wednesday's lecture. All right, so this should be an easier one. Like charges attract and unlike charges repel. Is this true or false? Like charges attract and unlike charges repel. True or false? So we talked a little bit about this and Coulomb's law on Wednesday. If this is something that you don't remember or you weren't here on Wednesday, you can always refer to that recording. I'm happy to stick around after class too if anybody has any questions. Sometimes I'm here half an hour later just to go through some of the problems. Don't mind staying late at all. All right, so where are we? We have 88 students. I'll give you about 10 more seconds. 89. Okay, does anyone in this room need a little more time? Raise your hand high if you want me to hold off for a minute. All right. So the answer, of course, is false, right? Good job. Every one of you got that right, so I will not review that. How about this one? This actually pertains to Coulomb's law. As the distance of separation between charges increases, electrical force A increases, B decreases, C stays the same. As the distance of separation between charges increases, what happens to the electrical force? And as always, this is about participation, everyone. So if you want to turn to your neighbor, perfectly fine with that. Discuss it, talk about it. When we get to 80, I'll do the countdown. All right, we're up to 80 students, so I'll give you about 10 more seconds. Who knew it was going to snow today? Whew. Walk outside, wow. All right, anyone in this room need a little more time? We will have another question, so don't worry. Okay, so I'm going to go ahead and close this one, and of course there's going to be an inverse relationship. So as the distance increases, the electrical force will decrease. All right, good job. Okay, so if this is something that you want to talk to me about after class, I'll certainly do that. Or if you're confused, yeah, just come up and ask questions. All right, so the last one here, actually I have one more after this, but it's more of a feedback, student feedback. So true or false? This one's a little more tricky. Typically, all cells at rest have a resting membrane potential between plus 20 and plus 75 millivolts. Is this true or false? Again, you can discuss it with your neighbors. Typically at rest, a cell would have a resting membrane potential between plus 20 and plus 75 millivolts. Is this true or false? Okay, we're already at 87. I'll give you about 10 more seconds. Does anyone in this room need a little more time? Okay. Just give me a thumbs up. If not, we can talk after class. Okay, that sounds good. All right, so let's go ahead and close this one. And the correct answer is, of course, false, right? Nice job. All right, so what should it be? Anybody want to raise their hand? What usually is typically the range for, yeah?
Negative 100 to negative 20.
That's right, negative 100 millivolts to negative 20. Perfect. All right, everyone got that right, so I'm not going to review. I do have one more question, though. After we learned a little bit about electrical force, we actually jumped right into the electrochemical equilibrium and the equilibrium potential, if you remember. We were able to do one problem. I think we all calculated the equilibrium potential for sodium together, right? Do you remember that? That was the very first problem on part 1, and that was A, right? Okay, so now that you know a little something about the equilibrium potential, I actually have one more question for you, and I just want to see where everyone is. Okay, so this one is more of a student feedback question. How would you assess at this point your understanding of the equilibrium potential? A, totally got it. B, I understood it when you were explaining it in class, but now I'm not so confident about its meaning. C, it's still a little fuzzy, I kind of get it, but I need some additional help. D, I'm a bit lost, and E, I'm not here today, goodbye. I can tell you that's not the right answer. No, none of them are a wrong answer, so don't be afraid. We will actually go through this again. I mean, I will review it. So if you have totally got it, at least you can maybe turn to your neighbor and really help them out if this is something that you feel like you've already mastered. Today we're going to start off by trying to decide which way those ions are moving. And that's always the number one question I have before exam 1. I have lines of people in my office, and that's the number one question. Which way are the ions moving? So we're going to go through that today pretty systematically, and I promise when you leave, it should be fairly clear. Now, it might get a little fuzzy when you get home, but when you leave this room, it'll be crystal clear. It's one of those things that you just have to practice and start running those numbers, right? That's why you have part 1 and part 2, because part 2 is just more of the same. Just help you practice. All right, got 90 students. How many need a little more time in this room? Did you get this one? Yes, okay. This will be the one that I take for points then. I wanted to take today's for points, so good. All right, so let's see how everyone did. All right, okay. I think there's a good Gaussian curve here. Actually, 2 people actually said, I'm not here today, goodbye. That's funny to me. Anyway, all right, so let's get started. Let's, dive right into this and figure this out. Okay, so we talked about Bernstein's hypothesis. Remember, he's trying to figure out what the resting membrane potential is all about, okay? And because the resting membrane potential was so close to the equilibrium potential for potassium, he thought his voltmeter was just not working properly, right? So he thought that only potassium was moving across the membrane and that the resting membrane potential equaled the equilibrium potential. That may not make a whole lot of sense, but it will on Monday. So again, this is all like putting little pieces together, adding on, adding on, adding on. Okay, so what we did is I rolled out this. I want to make sure that everybody sees where we're going with this. Right now, today and Monday, we are just going to focus on first the equilibrium potential and then focus on the resting membrane potential. And I gave you some idea of how to think about the 2 of them. The equilibrium potential, remember, is just a calculated value. It's just a theoretical value where the electrical work and the chemical work are equal in magnitude and opposite in direction. And if the resting membrane potential was exactly equal to that equilibrium potential, then there'd be no net movement of that particular ion. No net movement, okay? In a one-ion system, if only potassium was moving across the membrane, then yes, the resting membrane potential would equal the equilibrium potential. Okay? So it is the voltage required to prevent the net movement of an ion down its concentration gradient. That's the formal definition of equilibrium potential. It is the voltage required to prevent the net movement of a particular ion down its concentration gradient. And at that voltage, there's no net movement. So when I rolled this out, let me just go back. When I rolled this out, I had you think about it. I had you, if you remember, I'm not going to go back to the slide, but it was a slide that had sodium, high sodium on the outside, low on the inside. High potassium on the inside, low on the outside. And so the reason is, let's just take sodium for example. Remember, we calculated the equilibrium potential. It was pretty positive, right? It's plus 61 millivolts. So when the inside of the cell is really depolarized or very positive, what's going to happen is sodium is going to repel, and not actually, a lot of them aren't going to enter into the cell. They're going to actually be reflected because sodium is a positive ion. There's all these positive charges in the inner leaflet now. You can see how that prevents the entry of sodium. And then I asked about potassium, and there was a little bit of some confusion, right? So I want to make sure I thought about this on the drive home because I'm a total geek. I was like, how can I better explain that? And so if you think about it, right, this is a negative, right? Let's just forget this for now. Let's just say now we're focusing on potassium. What would the membrane potential have to be in order to prevent potassium from moving down its concentration gradient? Well, it would have to be fairly negative inside. Think about it as these negative charges now hugging. I thought about that. I was in a pretty good mood. Hugging potassium. No, you can't leave. And staying inside the cell, right? So the cell, this membrane potential would have to be fairly negative in order to prevent potassium from moving down its concentration gradient. Does that make more sense? If you're thinking about the equilibrium potentials, for sodium it'd have to be very positive. For potassium it'd have to be very negative. Give it a big hug. Don't allow for potassium to leave. Okay? Pretty good? So when we thought about that, you'll see that most of the time it always follows the same pattern, right? Usually, because of the concentration gradients, right? 0 millivolts here. Equilibrium potential for sodium is very positive. We calculated it as minus 61 millivolts. I'm sorry, plus 61 millivolts. Today we're going to actually finish this up too and figure out what is the equilibrium potential for potassium. Or no, it was chloride, wasn't it? Yeah, that first one. We'll work on that. So that's where we're going. Remember, this is how I want you to draw the graph. On the y-axis is membrane voltage in millivolts. And if you're wondering about the x-axis, eventually we're going to add time. Okay, so right now we're not going to add that, but y-axis is membrane voltage in millivolts. And we've already done the first part here. All right, so let's figure out, and then I'm going to give you some practice. Let's figure out how do we decide which way an ion is moving. All right, take a look at your question. What is the measured membrane voltage? Take a look at that question. It's either going to be in the question or you're going to learn about the chord conductance equation. You can actually predict the membrane voltage. On Monday we'll go through that by the chord conductance equation. But when you look at this, what is our measured membrane potential? And we're looking at 1A. Oh, yeah, no worries. Anybody else need a problem set number 2, part 1? Okay. What's the membrane potential?
Negative 65 millivolts.
Thank you very much, negative 65. So what I would like you to do is go to our graph that we've already started, and this one is measured, so basically we're going to use a solid line, and our resting membrane potential is equal to minus 65 millivolts. With me? All right, so here is how we're going to decide which way an ion is moving. First, you want to take a look at your reference. For sodium, your reference is your equilibrium potential for sodium, right here. That's your reference. The biggest mistake that I see semester to semester is students actually use the resting membrane potential as their reference. Don't do that. Put your finger there, put your hand there. This is your reference, the equilibrium potential for sodium. Now ask yourself, where does the resting membrane potential sit relative to our equilibrium potential? Is it more negative or is it more positive than the equilibrium potential? If you guys know how to use your microphone, you can certainly do that. If you haven't figured it out yet, you can play with it. It's about pushing a button, correct? Yeah. So what do you think? Is the resting membrane potential more negative or more positive than the equilibrium potential? Maybe it's hard to look at the graph yet. All right? So anything below this line is more negative. Anything above this line is more positive. So up here would be plus 100 millivolts. All right, so where is our resting membrane potential? Is it more negative or more positive?
More negative.
That's right, thank you. Yes. All right, so we're going to draw a cell. Our ion of interest is sodium. I always put it in the inside. Here's the concentration gradient, right? But we're really referring to this one inside. And it's more negative. Now this isn't a real membrane voltage, so don't get too confused. This is almost just like a parlor trick to help you. Put a negative sign because the resting membrane potential is more negative. These will attract, and sodium will continue to move into the cell down its concentration gradient. It will move into the cell down its concentration gradient. All right, another way to think about this. Here's the real thing that I want you to commit to memory. The electrical work is not sufficient enough to prevent the net movement of sodium down its concentration gradient. So it will continue to move into the cell. Want me to say that one more time? Okay, the electrical work is not sufficient enough to prevent the net movement of sodium down its concentration gradient. So sodium will continue to move into the cell. So I'm going to put a little in here. Now what this is really a balance of two forces. All right? If the resting membrane potential was sitting right at the equilibrium potential for sodium, the electrical work would equal the chemical work. Electrochemical equilibrium. But that's not the case. That's actually very rare. Anything more hyperpolarized or negative, the chemical work is greater than the electrical work. It's a balance of two forces. Think about it like a teeter-totter. The chemical work, that concentration gradient, plays a bigger role than the electrical force. With me? Pretty good? All right. Let's pretend now that I said in the problem that the measured membrane potential wasn't minus 65 millivolts. It was plus 100. Plus 100 millivolts. Measured, right? Solid line. Resting membrane potential plus 100 millivolts. This could happen under experimental conditions if I passed a current. I could force the membrane potential to plus 100, or I could open up a calcium channel, and that would pull the membrane potential towards the equilibrium potential for calcium, which is plus 119. Okay, so either way, now our resting membrane potential is plus 100 millivolts. All right, so now put your finger on the reference, equilibrium potential for sodium, that's your reference. You ask yourself, where does the resting membrane potential sit relative to my equilibrium potential? Is it more positive or more negative? It's more positive, right? More positive. So I put a little positive sign in our little thing here. I put a little positive there. Now sodium is a positive ion. I put a little positive sign there. Now sodium is actually going to be forced out of the cell against a very large concentration gradient. Now you can say that the electrical work now is greater than the chemical work. And the electrical force is so great, it's pushing sodium out against a large concentration gradient. Is it starting to become clear now? The equilibrium potential is that teeter-totter point where they're exactly equal. If it's more negative, then sodium's going to be moving in. If it's more positive, then sodium is going to be moving out. Okay? I hope that is clear now. Okay? And C, if you remember, is just generate a graph. And you've already done that by making this graph right here. So now you can actually do every single part of that question, A, B, and C. But I think what we could do right now is maybe take a look at chloride. You want some practice? Like I said, this is kind of a workshop today. Let's do chloride. I'm going to let you do it on your own for now. Figure out the equilibrium potential. Try to figure out which way chloride is moving. And draw that graph, draw a cell. Okay? I'll give you about 5 minutes. I'll answer any questions. Stay with 1, A, B, and C, but now we're going to actually do chloride. Do you all feel pretty good about the Nernst equation and using it? Anybody feel they need a little bit of help? I can come on over. Or you feel like you can use that pretty well? Okay. Here is the Nernst equation at the top if you need it. Or I'm sorry, here it is right here. The equilibrium potential for any solute is equal to RT over Z F natural log of that solute outside over inside.
Well, but then we have to know if there is
Yeah. So it should be that. Yeah, I'm just yeah. Yeah, do that for
Explain to me again why sodium's going into the cell.
Yeah, so it's going to have a tendency to go into the cell because that concentration gradient is it's large on the outside, small on the inside. And just if you're looking at the chemical force only, statistics will say that the probability is usually going to tend, the net movement is going to be into the cell.
Okay.
Okay. So basically, if the resting membrane potential is very negative compared to the equilibrium potential, then you can think about it this way. The voltage inside the cell is not sufficient enough to prevent that net movement into the cell. So it'll continue to go in. The chemical force is greater.
Yeah.
But if it's like plus 100 millivolts, that is a really very depolarized, very positive voltage. Then it's basically going to start to take the sodium inside the cell. It's going to repel. And it's going to start to force sodium out against a really large concentration gradient. So that's when you know that the electrical work is way greater than that chemical work. If it's going against its concentration gradient, then you know the electrical force is in play.
Okay, so because it is negative 65, it just doesn't have like the energy to repel it in or like away, so it's just going to go in.
Yes.
Okay.
Okay. So it doesn't have that positive charge. It's not enough. It's going to sodium will still continue to move into the cell.
Well, isn't it also because this one's positive and this one's negative, and they're just like going to attract each other? Is that not like entirely?
Well, take chloride for instance.
Okay.
Okay. So you might have a negative voltage inside the cell. But it's still more positive than the chloride.
Okay.
So even though you're going to put a little positive sign, it doesn't mean that the cell is positive. It actually means that it's just more positive than the equilibrium potential.
Okay.
So be careful with that. You know what I mean?
Yep.
It has everything to do with the reference, your equilibrium potential. That's the teeter-totter point.
Okay.
And if you tip it one way, it's going to go with its concentration gradient. If you tip it the other way, it's going to go against the concentration gradient.
That makes sense. Perfect.
Okay, great.
Thank you.
Yep. All right. Is everybody ready to get started? Do you want to go through it together, the first one? All right. I wanted you to at least kind of work it through yourself before I just gave you the answer. I feel like that's a lot more helpful if you try it first. All right. So let's go to our document camera. I'm just doing this on the fly with you as well. So let's just start off by drawing our graph like we did before. We already figured out that the equilibrium potential for sodium is plus 61 millivolts. Okay. 0 is just a value that we're just going to put on our graph here. Not a measured value, just dashed. We do know that our resting membrane potential is minus 65 millivolts. And now we're trying to know something about chloride, okay? We're trying to figure out what is the equilibrium potential for chloride. So the way I set this up, and let me know if I'm wrong, The equilibrium potential for chloride, which has a charge of -1, is equal to 8.3 joules per mole Kelvin. Multiply that by, we've got 37 degrees Celsius here, so you add 273, gives us 310 Kelvin, over, what's the Z? -1, right? -1. 96,500 coulombs per mole. Multiply that by the natural log. We've got an outside concentration of 155 and an inside concentration of 40, right? I tend to do this back end first. I divide this and then get the natural log. If you want to use log base 10, then you can do that, but you have to then multiply 2.303 to the whole equation. It's a little more complicated, but some people have asked me about that. So just to make it easy, we're going to use natural log, and then you write down your number here. Then go ahead and multiply this part of the equation, write down your number, and then I usually multiply those two together. Okay? So if anybody needs some further explanation, let me know. But what did you all get? Yes. So you probably got this. You probably started off getting negative 0.036. Remember, it's going to be in volts first. Kelvins are going to cross out, moles, millimole, and then you're going to be left with joules per coulomb, which is a volt. We talked about that on Wednesday. All right, so that, if you multiply that together, right, by 1,000, if you multiply it by 1,000, you're going to get -36 millivolts. Everybody good with that? You feel pretty good about that? Okay, good. I see a lot of heads nodding up and down, so that's great. Okay, so let's go back. Ta-da! We already have our graph started. Now we're going to add the equilibrium potential for chloride at -36 millivolts. All right, so what do? Draw a cell. I like to put the chloride gradient in there. Pi chloride outside relative to the inside. That's the gradient. Now, here's the hard part. Here's the reference. I've got my finger on the reference. You ask yourself, where is the resting membrane potential? Is it more negative or more positive? It's more negative, right? More negative. Anything below this line is more negative. Anything above this line is more positive. So I put a little negative sign there. Chloride is a negative ion. In this case, it's actually going to repel, and chloride is going to be moving out of the cell against its concentration gradient. Okay, so the answer to B is chloride will move out. And this is the net movement. I better make sure that everyone knows that. Chloride will move out of the cell. Now, just looking at this scenario, is it the electrical work or the chemical work that's greater? Which is greater, the electrical work or the chemical work? It's the electrical work. If it's going against its concentration gradient, then you know the electrical work is in play. So in this case, the electrical work is greater than the chemical work. Electrical work is greater than the chemical work. And you already drew your graph, so you've answered that entire question. How does everyone feel now? Remember, the equilibrium potential is where the electrical work equals the chemical work. And these two forces are exactly balanced, right? Like a teeter-totter. And there's no net movement. Okay? Yes, question? So is sodium moving? Ah, great question. All right. Is sodium moving? If the resting membrane potential is not sitting right on top of the equilibrium potential for sodium, then you know there's net movement, okay? So in this case, both sodium and chloride are moving. Sodium's going to be moving in, chloride's going to be moving out. Yes?
So for sodium, would it be the electrical word would be less than?
Yes, right? You have to do it for every ion. So with the resting membrane potential being at minus 65 in both instances, it's not sufficient enough to prevent sodium from moving down its concentration gradient. But it's very sufficient, even overwhelming, to move chloride out of the cell against its concentration gradient. You have to take each ion separately. Yes? Yeah, perfect. Now remember, this is for every single ion moving across the membrane. Okay? So I think we're doing really well. I think what we're going to do is keep moving on. We'll finish this up on Monday. I do have a little bit of time that I want to blow your mind on this computer simulation. I actually really love this computer simulation. Do you all remember this graph? Remember when I talked about it, I said, commit it to memory, you'll see it again. Right? Does everyone remember this graph? Yep, okay. So this is actually looking at diffusion over time of uncharged particles. Uncharged particles. So what we're looking at, there's 3 different time points. On the graph, it's the very beginning. It's right here, B, and then right here where you've reached diffusional equilibrium, right? So in the beginning, there's basically all of the molecules are in compartment 1. None are in compartment 2. You see that in the very beginning of the graph. Then over time, some of the molecules are filtering in from compartment 1 to compartment 2 until they reach diffusional equilibrium. And we actually said that the change in concentration can be depicted by an exponential function of time. Okay? Pretty good? So commit this to memory. Let me just show you this very awesome computer simulation. Now, I'm very sad because the professor that maintained the site, he must have retired or something, and you can't access it anymore because it's not compatible with our. So about 3 years ago, I actually was able to capture it. It's a little glitchy still, but at least I was able to grab it, and I thought it was brilliant. Okay, so let's see here. This is ours, 3301. We're going to go into it. If you actually go to our cell physiology and go to the tab where it's diffusion of charged particles, it's under that one, because we're going to do diffusion of charged particles too. You'll see Wednesday's lecture. I did post that already. Keep going down, and it should be right there, okay? So you can take a look at it. It is, I'm going to turn the sound off, and I'm going to narrate it, but I did narrate it at one point. So let's full screen it. There we go. All right, so I'm going to start. Oh, it's already started. So what it is this is actually a computer simulation of uncharged particles first, right? Here's my arrow. I'm telling you about it. You can start the simulation and then open a channel. You can see there's no channel open at this point. The volume is finite, so it's not an infinite volume. It's kind of confined to these compartments. And I've clicked on uncharged particles. Okay, uncharged particles. In this simulation, you can see that the outflow you'll be able to see once I open a channel, and the influx you'll be able to see as well. This inside compartment is about 200 millimole, and then the outside compartment is only 20. So it's kind of like, a simulation we've talked about with glucose, right? These are uncharged particles, and as soon as I open the channel, you can probably imagine that the net diffusion is going to go from inside to outside, right? Until diffusional equilibrium occurs. So in just a second here, I'm going to open a channel in about 10 seconds, I can see. All you do is click that open channel. Doop, click, come on. There we go. Open the channel up. Okay, so now you can see the channel's open. You can actually see the outflux and the influx. You can see the concentrations are changing, right? Until you get about the same concentration on both sides, and you can actually say, okay, I've reached diffusional equilibrium. So this is uncharged particles. Pretty good? All right, so you can actually plot this. Just click on plot. And it's the graph that I showed you, right? So you can see over time, the change in concentration is going to be depicted as this exponential function of time. So you reach diffusional equilibrium, and now it's going to bounce around a little bit, but basically we're now at diffusional equilibrium. Okay? So now, since we know a little bit about electrical force, let's do this again, but what we're going to do is we're going to look at charged particles, okay? And we're going to see how those concentrations change. All right, so need to stop this simulation. We're going to keep the volume at finite volume, but this time we're going to click on cations. Okay, so we had to close the channel, start it up again. Finite volume, start it up. Okay, notice that there's no ions moving across the membrane. So the membrane voltage is 0. Remember, you can't have a membrane voltage if there's no ions moving across the membrane. So channel's closed, membrane voltage is 0. We've got 200 millimole in the inside, and we're only looking at like the red ones. This is like potassium. We have 20 millimolar on the outside, right? You can take a look at the outflux and the influx. And again, the membrane voltage is at 0. So now, open a channel. You could actually calculate where you think the resting membrane potential is going to be just by plugging in the Nernst equation and calculating the equilibrium potential with 200 millimolar over 20 millimolar. It would probably, as you already know, be about minus 60 millivolts, 61 millivolts. Okay? So, when we actually hit that open channel, doink, now you can see the membrane voltage is changing, moving towards minus 61 millivolts. Awesome, just as we predicted. Now take a look at this. Blue ions are lining up at the membrane, red ones are lining up at the other membrane. The membrane is starting to act as a capacitor, and now that electrical force is coming into play almost instantaneously. So we're at minus 60. We're bouncing around minus 60 millivolts. Charge is being separated right at the membrane. Okay, now let's take that plot. Here's the kicker. The concentrations don't change because almost immediately the electrical force and the chemical force balance, right? In a one-ion system, the resting membrane potential becomes the equilibrium potential, and there's no net movement. That's actually really significant. Again, concentrations are not changing when you open up that channel because immediately the electrical force and the chemical force are exactly equal, balanced. So what's the significance of this? When we actually get to neurons, okay, think about this. When you open and close sodium channels and potassium channels, it's not about changing the concentration, right? So the pump isn't working overtime to reestablish those gradients. There's no concentration change, okay? Very few ions have to move across the membrane in order for you to get sweeping changes in membrane voltage. Okay? So that's an important concept. Very few, I'm talking 10 to the minus 13 particles. Very few ions have to move across that membrane in order for you to get these huge changes in membrane voltage, like an action potential. Action potential can go from minus 70 millivolts to plus 50 millivolts, back down, okay? So we're going to talk about the ionic basis of the action potential a little later. But that simulation is really great to illustrate that there are not changes in concentration when you open and close this. So the action potentials are only due to changes in conductance, just opening that channel and closing it. Opening, closing it. Concentrations aren't changing. It's just changes in conductance. All right? So we're going to keep going with this question. Did you have a question? No. Anybody have a question so far? All right. So how are we doing? We have 3 more minutes. Let me just give you a preview of where we're going on Monday, and then we should finish this up and move on to next Wednesday. We'll be talking about active transport. So hold on just a second. Let me just show you where we're going. Next time, we're going to concentrate on Ohm's law and the resting membrane potential. All right? So here's where we'll pick up. I'm going to be talking about Ohm's law only because I talked about what conductance is, right? I'm going to talk to you about conductance. It's just a pathway for an ion to move across the membrane. It's the inverse of resistance. And if you want to think ahead, I would say focus on this particular slide. It's just one slide. This is Ohm's law. It says driving force, which is the membrane voltage minus the equilibrium potential, that's the driving force, is equal to current times resistance. So take a look at this, okay? And on Monday, we're going to pick up with Ohm's law and the resting membrane potential. All right? I'll stick around if you have any questions, but have a wonderful weekend.
Hi.
Hi.
Okay, so I have a question about number 3.
Okay.
C. So, kind of figured it out, but I'm just still going to ask. So, like, it says, what will happen to the equilibrium potentials if K is... So, are we just meant to, like, probably, like, add 25 to this one and then to try 25
and then
and
what will you have to do?
recalculate?
Yeah.
Okay.
It's kind of tedious, but that's exactly what you have to do. Thank you. Yeah. Hi.
So my top hat wasn't working
Oh,
for the first
yeah.
couple.
Okay.
But then it worked for the last
If
2
you
or
got
so.
the last one,
Okay.
you're good.
I'm good?
Yes.
Okay, I got
yeah.
that one.
Okay,
Thank
great.
you.
Yes.
Okay, hi Melissa. I'm
Hi.
still a bit fuzzy on this today.
Okay.
Is it possible to meet?
Yeah,
before class on
absolutely.
Monday?